Hello, my name is Bruce Momjian. I work for EDB. We have a new logo this week right here. So this is brand new, kind of cool. The other thing I'm excited about, which is more of a typesetting geek thing, but I never liked this like QR code because it was always really dark. So I found out how to edit the EPS file to make it kind of grayscale, to kind of push it back a little bit. So typographically, that's my excitement. I am one of the Postgres core team members. We're really enjoying the conference here, and I'm here to talk to you today about AI. This presentation, along with 62 other presentations and 129 videos, are actually at this website right here with that QR code that I just talked about. So if you're curious about this presentation or others, feel free to look at that. I do like giving this talk. It's very rare that I get to talk about philosophy as part of a Postgres talk. And it's very rare that I get to sort of look at decades of computer history and sort of trends that we've seen from my lifetime and even kind of before related to AI and sort of understand where are we in that context. Because talking to people in the hallway, there's just a lot of confusion about what AI is, why is it new, what is it exciting, and I'm hoping to answer those questions during this talk. And also to talk to you a lot about Postgres and how you can do AI in Postgres and give you a pretty weird but cool demo about it. So we're going to talk first about what is artificial intelligence, sort of to set the baseline. This is where the philosophy part comes in, because you have to understand what your goal is if you're going to achieve it, right? So a lot of people with AI have sort of a muddled goal of exactly what they're expecting. So again, that's good to go over. Then we're going to talk about some terms in the second part, particularly machine learning and deep learning, and sort of go into that. There are a lot of URLs in this presentation. You may not be able to obviously write them all down, but if you download the slides, you can click on any of the blue text, and it'll take you to that website or that video to watch it. Third section is the most unusual. It's actually a demo of doing AI in Postgres using PL Perl. This is not a demo that you would actually use in production, but I think is very illustrative of sort of how AI works. Then we're going to get more practical. We'll talk about hardware and software and how they relate to AI. We'll talk about tasks that are popular with AI, and finally, why use a database. Finally finishing it out. Okay. So let's get started. This is actually a definition from Wikipedia, and what I'm going to highlight here is that AI is something that mimics cognitive function. It's not necessarily cognitive function, but I'll talk about that a little more in this section. And it is associated with things like learning and problem solving, but again, is it the same? Is it not the same? That is really a fundamental question when you start to understand what our goals are with AI. And if you can't answer the first question, it's kind of hard to answer the second one. I love this quote. And actually, this is the philosophy part. And I don't know if any of you have thought about this. I have actually thought about this. Actually goes back centuries of how people thought about human intelligence. But the concept is that if the physical world is all that exists, like physics and chemistry and however our brains work and so forth, if that's all that exists, then human intelligence is only different from machine intelligence because of its origination, okay? And what that effectively would mean that a computer could be intelligent because it's no physically different than a human brain. It's just created differently, right? But there's a corollary to that, and that actually is that if the physical world is all that exists, then effectively human will is also an illusion, because what we're doing, what we're thinking, the words coming out of my mouth are really a program of the chemistry in my brain, and there's nothing really that is me. It's just a process. And therefore, you start to get into cases where you create a computer. Is that a human? Well, not in the way it originated, but is it intelligent? I guess, right? So I don't necessarily subscribe to this concept, but it's what's interesting is as soon as you decide the physical world is the only thing that affects outcomes, then effectively you don't have free will anymore. This is decades old. This is centuries old. This is not a new thing, but it does relate to AI and our expectations for AI. Okay, and I have an interesting Atlantic article there that kind of goes into this in much more detail. The history of artificial intelligence is kind of checkered. We're in a sort of AI renaissance, I would say, right now, and I'll talk about why that is a little later. But there was AI even before computers, the concept of pre-computer philosophy. I think Descartes was a big guy with this kind of concept. And then they used to think of AI as something that looked like a human, so robots or things that moved like a human was somehow AI. Then we have the Turing test, the concept that could you tell from a discussion whether that person was a real person or a computer. Then we got into expert systems. This is something that happened in the 80s, and in fact was a pretty poor outcome in terms of AI. It had a lot of promise, a lot of buzz around it. My former boss at EDB actually got a doctorate in expert systems, and the concept was that you would talk to an expert, you would record how they would make a decision, and then you would encode that in a computer, and that's how you would, solve a problem. But obviously, the people are not super accurate at that, and as circumstances changed, you had to reprogram it. It didn't go too well, and in fact, then we go into what is actually known as AI winter, which is somewhere between the 90s and maybe 5-7 years ago, where effectively there was very little interest in AI at all. And then you have where we are now, and I think ChatGPT and OpenAI kind of sparked that. But I'm going to talk a little later about why that is, why that happened, and why it may not be as sort of groundbreaking as we think. I've always felt it's like fusion energy. It's always 10 years away. I was in the 70s. I was told it was 10 years away, and it feels like we're still there. But we'll see. We'll see where things end up in terms of AI. Okay. I have two quotes from somebody at Microsoft. I'm just going to read it. In a certain sense, I think the artificial intelligence is a bad name for what it is we're doing. As soon as you utter the words artificial intelligence to an intelligent human being, they start making associations about their own intelligence, about what's easy and hard for them, and they superimpose those expectations onto the software systems. I think this is very true. Again, what are we going to accomplish? Another quote, algorithms are just math, and one of the math functions is to simplify the world so our brains can tackle more otherwise dizzying complexity. The software we call AI is just another way to arrive at complicated mathematical functions that help us do that. And again, Wall Street Journal article here. The concept, again, back to what we were talking about before, is the intelligence that we're actually working on the same type of intelligence that we have, or is it just mimicking that? And I can't answer that question. You need to decide that yourself. But it does impact our expectations for AI. Okay. Any questions? That was the philosophy part, as you can imagine. Okay. No questions? Okay. All right. So let's get into some details. I think this is kind of very illustrative. This video actually right here is fantastic. It's a 3-hour MIT video about artificial intelligence, and he goes through a lot of the details of how these systems are set up, the kind of goals they have, and so forth. So feel free to look at that. The concept is artificial intelligence is a grab bag of a bunch of different technologies. Machine learning is the most popular one right now of that subset. And I'm going to show you what machine learning looks like later in the demo. And then deep learning is sort of, again, a subset of machine learning. Okay, but there are other AI aspects out there. But again, that's sort of the way that they work. So this is actually what machine learning looks like. And machine learning is most of what we do now for AI, whether it's image detection, voice recognition, ChatGPT, these are all basically machine learning kind of setups. And the way they normally work is that you have something called a tensor, which is basically a collection of something called neurons. Now, there's been criticism of the concept of neuron because it's trying to associate with the brain, but it's not super accurate. But we're just going to use the term that it comes with. So the way that machine learning works is you start with a tensor, and the tensor has several neurons. In this case, it's just 3. But again, this is very ridiculous. You'd have maybe hundreds or thousands or millions potentially of neurons here. And then what typically happens is you take some training data and you put it in and you feed it through the tensor. And all the neurons measure the training data as it goes in. And what happens is it sets the weights of each of the neurons. Okay? Now, I know this is very abstract. I'm going to show you a specific example later, but just follow along here. We've got 3 criteria that we can measure of the test data, basically. And based on the test data coming in, we set the weight of how important each of these neurons is in the test data. And once we've fed the training data in, we can then start to use the training data. Notice in this tensor, the weights of the neurons are different. And the reason they're different is because the training data set them that way. Okay? And this is where it really contrasts with expert systems. Because I mentioned before, expert systems, you'd interview somebody, they would tell you how important all of your metrics were, and you'd code that into your expert system. In this case, we're not interviewing anybody. The training data itself is setting the weights for the neurons, okay? And that's really what it's called machine learning, because the machine is learning or setting weights based on training data, okay? There's 3 types of machine learning, and I'm going to go through each one. This one is probably the least popular. It's basically called unsupervised machine learning. You put a bunch of data in, but you don't have any results with them. There's no you basically imagine you put in pictures of cats and dogs, and you ask the system to somehow distinguish between the 2, but you don't really tell the system which one's a cat and which one's a dog. And then you basically use it at the end, okay? And again, this is not used as much. I do have a nice URL here to learn more about it. This is the most popular. It's called supervised machine learning. This is where you have training data, but you also have results. So when you feed a picture of a dog in, you say it's a dog, a cat, a turtle, or whatever. And then what happens, you get different neuron settings for cats and dogs and neurons, and then when you put the data in, and then when you finally use a result. The third one is the most complex. This is where you're using training data with results, but you also want the way of adjusting the machine learning over time. So for example, if you're doing fraud detection, and I'll talk about fraud detection later, what happens is over time you have different fraud methods. So you want to feed back, an example, you might have initial state, you send a bunch of results in, some fraudulent transactions, some valid transactions. But over time, you want to be able to feed in when a wrong result is made, you feed it back in and you relearn the system. There's a whole bunch of mathematics around this, retraining, getting the results back in and adjusting existing data models without running through all new training data again, but making small adjustments to it. And I'm not going to get into this. I don't even have a URL for this. There's so much around this. But a lot of times, frankly, when you set up a machine learning model, modifying that machine learning model over time and not over modifying it is a huge challenge. Okay. This is deep learning. And what deep learning is, it's a case where you have a single machine learning, but then you pass every one of the neurons to every one of the neurons in the next stage of another machine learning. And then that one passes to another machine learning, okay? And this you would see, for example, if you're doing image recognition or you're doing voice recognition. This might be the volume of the voice. This might be the pitch of the voice. This might be the speed of the words, right? And then you want to have your words, and then you have to determine the meaning of the words as you go forward. So you have, or it's an image, you might do color detection here. You might do edge detection here. You might do shape detection here, okay? And you can see where you start to layer these models to start to mimic or basically do AI with more complicated cases. You basically take a single machine learning and you build that to the next one and the next one and the next one. This can be very computationally expensive, obviously. This is why there's so much compute required here. And again, we have a URL for that. Okay, any questions? Wow, okay, cool. All right, good. So this is the demo part, and I'm going to make an apology. It's the demo. It's not like, something you're going to put in production. But I tried to pick the simplest case. And I basically said, okay, let's make a machine learning that can take a number and predict whether there's a 0 in the number or not. Now, I know I can do that mathematically. It's not hard, but I didn't want to do it that way, right? I wanted to do it in a machine learning way so you could kind of understand it. So for example, the first one is true because there's a 0 in there. And the second one is false because there's no 0 in there. Okay? Pretty easy to understand. So how are we going to do this? Well, we're going to first create, we're going to install the extension PL-Perl. I chose Perl because it fits real well on the screen, right? You can kind of compress it down to a couple lines, and it's really easy to see. If you want to run this yourself, download this, go to this URL, pipe it into PSQL, and the whole demo will just shoot down on your screen, okay? So a lot of presentations I have used that method, and this happens to be one of them. Okay, so the first thing we're going to do is we're going to do something called generate a tensor. Do we remember what a tensor was? Tensor is the thing that holds the neurons, right? In this case, our tensor has 11 neurons. I know this is Perl, it's a little confusing, but the basic idea is that we have a different neuron for how many digits are in the number. So the longer the number of digits in the number, the more likely there's going to be a 0, right? Right? Because if it's only 3 digits, it's less likely. If it's 7 digits, it's more likely to have a 0. Secondly, I have an 11th tensor, which just tells me, is this divisible by 0? So obviously, if it's divisible by 0, then it has a 0 in it, right? So that would be an easy one, right? So I'm basically going to create a tensor with these 11 neurons, okay? And then I'm going to have true or false, obviously, depending on whether it's that. And I'm going to basically encode an array that I'm going to return here in PL-Perl, okay? Then I'm going to create my training set. Remember training set? We talked about how you train the machine learning. So I'm going to pick 10,000 numbers, and I'm going to generate, and this is a little weird math, but the numbers are going to have a random number of digits. I'm not sure. It took me a while to understand, but if you just generate random numbers, they're all going to have pretty much near the maximum number of digits. Just that's the way it works. But if you write it this way, then you get a lot of short numbers, a lot of long numbers, right? And that's kind of what we wanted for this example, okay? So we're going to load up a table called training set with 10,000 numbers, and we're just going to insert it into a table. And this is a common table expression, pretty easy to understand. Okay, so this is my training set. Here's my numbers. You can see I have 2-digit numbers, 3-digit numbers, 4-digit numbers. And here's my tensor with the neurons, okay? Right, because we kind of ran it through and we decided how it was, okay? So then we have something called a weight. Remember the weight? The weight was the thing that goes up and down in the neuron. Remember the little slash thing? And as you train it, it does that. Well, we're going to create a PL-Perl function that effectively computes the weights as the data is coming in. It adjusts it depending on what data we get loaded in, okay? And this is the end of the function. And then we're going to do something called a tensor mask. So this allows us to mask out only the neurons that make sense for us. And we also have a way of summing the weights, because remember we have 11 tensors, so the total predictable value is the sum of all the tensors, not just one of them. And then we also have to use a softmax so we don't go over 100%, so we kind of balance it to zero, from between 0 and 1, basically. These are all pretty standard terms in AI. And then we basically create a table with all of our true numbers that have a 0. And then we create another table with another set of data that has all the cases where there isn't a 0 in the number, okay? And then we basically, so this is our, the weights for, so this is what we're doing is we're generating the weight as we run through our training data for all the falses. So here's where we're actually doing the training and setting the neurons. And here are the neurons, 11 of them, for the true result and 11 of them for the false result. Then we're going to actually run an example. In this case, I'm going to put the word 100 in. Let's see how likely it thinks. So it thinks there's a 22% chance there's a 0 in there. Okay, all right, it didn't work too well. If I do 101 now, that's interesting, that drops to 11%. So we're getting a little closer than being off, right? How about if I pick a big number like this? Now this is also way off, so this is a really big number. There's a lot of digits. It thinks, oh, there must be a 0 in there. Yeah, 68%, 69% chance there's a 0. No, there's not a 0 there. Okay, so anyway, this is not wonderful, but you get the point. I can actually run a test with 1,000 numbers, and I can kind of run it through a query, common table expression, and I end up getting how reliable, how accurate it is. And it basically says it's like 72% accurate, and it's kind of plus or minus 15% roughly. When you do a lot of data, I just happen to pick bad numbers or who knows what. But you kind of get the data. You can see the concept that you're loading data, you're creating the neurons for the tensor, you're loading your training data in, you're setting your weights, then you're actually using the result, and you're putting the number in, and you're running it through the machine learning, and you're getting an output. Is the output great? No. But again, it is illustrative of how inaccurate, I guess, AI could be as well. Okay. Any questions? Yes, sir. So the question is, how did it come up with the weights? So the way it came up with the weights, and I'm going to go way back here. This is why I like slides. Remember generate weight? Yeah. Okay. So what it's doing is it takes our 10,000 numbers, and it basically looks at, so with the 10,000 numbers, I know which of those 10,000 numbers have a 0 in them and which don't have a 0 in them. Very similar to me sending in financial data. I know which ones are the fraudulent charges. I know which one the valid ones are. So I know in my training data which one it is. This is a supervised learning, remember, where we have not only the training data, we have the results. So we're putting it in, and every time we put a true in, we're looking at the neurons for that true, and we're setting the neuron weights for the true state. And then we're doing the same thing when a false one comes in. So then when one comes in, we run them through the weights of the neurons, and we get basically a statistic result. Okay? Now, this is not a reinforced learning. So when we get it wrong, the weights don't change, right? But this is how they were set by the 10,000 numbers that we put in. Okay? And those are literally the weights for the numbers. And in fact, let me see here. So in fact, this first one is almost not even significant. And you can see the numbers as they go, they start to get a little funny. And then this 6-4, this is the one, I think that's the last one that's for the, whether it's divisible by 0 or not, right? Like, and I thought that would be pretty predictable, but I don't know. This is actually part of the problem, that when you do this AI thing, you don't really know why some of the results came out. And this is a little scary part when they're talking about hooking up AI to safety systems, right? You're like, well, I don't know, right? Because even the people who wrote the tensor, wrote the neurons, put the training data in, they know how the numbers got there. But they're not necessarily, they'd have to go back and look at every single training set that they put in to figure out why it behaved that way. Great question. Yes, sir. Yeah. So the question is, when you're creating deep learning case, so in this machine learning case, we know what the layers are, right? In the deep learning case, what you're doing is each layer probably has another. As I understand it, people know what the neurons measure, but they're not sure, because once you get to, and I'm going to go way back, and this is where it gets really interesting. So what's really interesting is that every neuron feeds into every other neuron, okay? And the problem is that you're basically saying, well, when this is true, it may have a big effect on the top neuron that we didn't anticipate at all. Okay, so we kind of know what the layer's doing, but we don't know the interaction between the previous layer and the next layer and the next layer. So for example, if you're identifying a dog versus a cat, is the shape of the face is a little different, the color may be different, the size of the eyes may be different. So again, it's hard, it's depending on which layer you're looking at. You kind of put in a guess, kind of, but you don't, that's part of what I was telling the other gentleman, you don't really know how that layer is being affected by potentially previous layers that you have. But,
how do they decide how many layers?
Well, that's the thing. You have to define, so the question is, how do you know how many layers? You have to define the number of layers, and you kind of have to define what each neuron measures. You can't necessarily just throw it together and just, as I understand it, you can't just throw it together and just run the data through and hope to get the result back. You kind of have to structure exactly what you're measuring. So for example, if we're doing an image, edge detection, are there, is there patterns? What colors are in the image? How big is there one big color, or is there a lot of little colors? So yeah, it's kind of crazy. I mean, if you think, for example, Hugging Face, which does identification of people. So you can take a picture. This is a person. Okay, how do I know what another person is? So one part is measuring the distance between the eyes, another one is measuring the distance between the mouth, and and then each layer is doing its own measurement, and then at the end, it's going to predict who it is, right? It's like kind of crazy that it actually works, right? And you're right, they don't kind of understand this. Once you get into machine learning and you're feeding, not only are you feeding from this neuron to this neuron, but you're feeding from all these neurons down, it's like, yeah, it gets really crazy.
On your demo just now, I don't quite get an answer. How do we, I guess, the same question, right? How do you adjust these weights? I was under some kind of impression there is, you calculate some kind of standard deviation from, because you're a supervisor, that you know what's wrong. You sort of measure the distance between standard deviation between the error and the correct, and you use a greedy descent, right? This is like a derivative to see, hey, what kind of combination of weight give me the sharpest path, right, to that gradient. Is that something applicable here, or?
It's actually this softmax. So what softmax does is that these weights are all, they're not bounded to a span from 0 to 1. They're just weights. So when you pull the number through, you're going to get who knows what number. And what this does is it kind of takes all it takes all of the weights in all of the neurons, and it balances them so they all equal 1. And then that way, when you run it through, you get a statistics between 0 and 1, because if you hit 100% in all of them, you have certainty or predicted certainty. But anything else, so what softmax does is it's basically pulling everything down. It's computing the sum, and then it's pushing that down to basically push them down to 0 to 1, basically. Okay? Other questions? Okay. So I know we're covering a lot of area here, but I think it's important and I'm trying to do my best, having spent quite a bit of time studying this. So let's talk a little about hardware and software efficiency here. Postgres supports, you can do a lot of work in Postgres with AI. We have MATLAB, which is different than MADlib. How many of you remember MADlib from the 70s? But anyway, I used to think that I remembered it wrong, and I was like, I thought it was called MATLAB, and then I see MATLib. Oh, okay, that's what it's called. I thought it was called MADlib, and then I see MADlib, I was like, I thought it was called MATLAB, and I was like, no, they both exist. Scikit, TensorFlow used to be the big one. I'm not sure how popular that still is, and Weka, which I don't see a whole lot about. But those can all be done at the client side, and again, we have a URL here. Dave Page also is here, and he's done some work on this as well, so feel free to bug him if you see him. And then you can also do the AI on the server side, which is, again, kind of unique for Postgres. So again, MADlib, PL/Python, Scikit, pgvector, all work at the client, at the server side. pgvector, obviously super popular, but again, really all it is what did you see previously? You saw a lot of vectors, right? So all pgvector is really doing is just a souped up Perl, if you want to call it that, to do vector operations, and it's optimized and so forth. You wouldn't do anything. You'd never run this in production. But again, when you're starting to look at something like vector AI, then it starts to make sense. Also, particularly if you're doing RAD, where you're basically feeding your data through a filter before you send it off to maybe OpenAI or another AI toolkit. A lot of people use Postgres for RAD, meaning that you filter your data, you maintain the state of the session and the previous questions maybe that were asked in your database itself, and then from there, you send it out to an AI engine that may not be done in Postgres. So in fact, pgvector, and Jonathan Katz knows a huge amount about that. So feel free to bug him as well. Hopefully people are not telling other people to bug me. But anyway, that's actually the big pgvector. Not only can you do AI, but if you're doing pre-processing before it goes into the AI, that's where you see a huge amount of pgvector work. And again, we have a URL right here. The reason GPUs are so popular, somebody was just talking to me an hour ago about NVIDIA being as bigger than 10 huge companies in terms of valuation. This is very computationally expensive, particularly the deep learning case, because you may have if you have 1 million neurons and 1 million neurons, you have you have 1 trillion. Yeah, so you have 1 trillion. No, yeah, you have 1 trillion computations here. So again, this gets to be very, very expensive, and not necessarily something you want to do on commodity hardware. So again, this is one of the reasons you start to see GPU work, because it can do a lot of parallelism that works really well with GPUs. Okay, any questions? Okay, let's talk about tasks. So we're going to be really kind of concrete here. The classic use, I remember of AI as a kid, was chess. They had little computers that would play chess, which I thought was kind of amazing. How many of you remember Deep Blue playing Jeopardy? That was super popular. But it's kind of odd, because Deep Blue, as good as it was at chess and as good as it was at Jeopardy, IBM eventually sold it off, maybe 8 years ago or something. They probably regret that now. But ultimately, the tragedy of Deep Blue is that, I'm not sure how many of you were in the industry at this time, but if you talk to people who they basically tried to deploy Deep Blue in a lot of situations, and they got very few successful deployments. So there's a cautionary tale there of sort of over pivoting, because as amazing as it was at chess and Jeopardy, IBM tried using it in a lot of companies. You can imagine when your computer beats Jeopardy, a lot of companies are interested. But they went about 5 years doing a lot of deployments and really had very few successes. That's why they sold it off. So it's interesting, I think, anyway. We do use AI now, things like voice recognition. Certainly search uses it. Recommendation engines use it. Image detection, we've talked about that. And weather forecasting, it's been used for decades for weather forecasting because weather forecasting is very computationally intensive and very easy to sort of imagine I'm doing that weather tensing. Well, okay, I set my neurons, right, for like barometric pressure, cloud cover, and you know what I'm saying? They can predict the weather based on these AI models. It kind of makes sense, right? And that's how we do a lot of weather forecasting now. I'm going to go into a little more detail about a specific use case here. This is a fraud detection. I kind of like this example because I think it allows you to show you some of the detail. So these, these 7 bullets would be my neurons, okay? So I'm going to do fraud detection, and my first job is to figure out what do I want to measure about these transactions? And I just picked 7 things I thought would be reasonable. Now, years ago with expert systems, we would go to people who worked in the industry who did fraud detection, and we would ask them, how important are these? But the problem is, A, they don't probably know that accurately, and B, the fraud activity would change over time, and they can't necessarily adjust to that. So I picked, for example, how big the charge is. That would indicate maybe fraud. Whether it was a swipe, a chip, a PIN, or an online charge might be important. How far the vendor was from the chargee's billing address, distance of the charge from the last charge, that might be interesting. The country the vendor's in, the previous charges to this vendor for chargee, and maybe previous fraudulent charges by the vendor may also be useful, okay? So how would I actually, and then again we have a video here, how would we implement this? Well, first we chose the attributes, which were 7 of them I showed you, and then we're going to create machine learning neurons to measure each of those, okay? And then I'm going to create some training data with the required attributes for each transaction and its outcome. Is it a valid or an invalid transaction? That's my training data. It's supervised because I have results, okay? Then I'm going to feed the training data into the machine to set the weights of each neuron based on how much each neuron's attribute predicts the validity of the fraudulent intent. This is where the neurons go up and down the weights go up and down as we're feeding data into the system. Then I start feeding real data in the system and I get results. And then ultimately, if I'm using reinforced machine learning, then I'm going to potentially feed correct and incorrect results back into the neurons to improve the accuracy of the weights and to adjust for changes in the environment, okay? So I see this as kind of putting everything together. You can see me setting up the weights. You can see me first I have to set up the neurons and what they measure. Then I set the weights. Then I feed the training data in with the results. Then I feed the real data in. And then if I'm using reinforced learning, I'm adjusting those weights over time. Does that make sense? It was not easy to get to this understanding for me, but I think it's a good example kind of showing you how you would walk through a lot of these examples. Now, why use a database? Why Postgres? What does this have to do? Well, historically what happens, and this is true in the database, been true in the database industry for years, is that when a new technology arrives, it typically arrives outside of the database. Whether it's data warehousing, full-text search, GIS, JSON, they're all usually, Dave, have you been here the whole time? All right, we're going to ask him right there. There's your guy right there. All right, good. So I can point at him and just everyone can talk to you after the meeting. Great. I'm sorry, I didn't catch that. So what was I saying? Yeah. So basically, what happens is that the new technology starts outside the database. And over time, there's this concept called data gravity, that people don't like shipping huge amounts of data all over the place because it's hard to synchronize, it gets inaccurate, it loses sort of its structure as it gets out of the relational database. So the concept is that over time, a lot of this data moves in, a lot of these external things that we thought could not be done in the database eventually are. And because of Postgres' extendability, which is one of its greatest assets, one of the reasons Postgres is so popular, one of the reasons we have so many conferences like this, is because of that ability to bring things that typically were done outside, inside to the database. So why would you necessarily do that? Machine learning requires a lot of data. Your data is probably already in your database. So certainly your training data would ideally be coming from your database. And why not do it there if you can, okay? So the advantages, for example, you can use the previous activity as training data. You have seamless access to all of your data. You can actually do something like, I will not commit this transaction if there's a high probability of fraudulence. Right? So right at the date, even before you commit a change, you can actually do a check, for example, for fraudulent and abort the transaction if it turns out that the data comes back with too high a probability of being fraudulent. It can, the AI data can be in the database. It can benefit from concurrency and backup. And of course, you may have needs like I need to know how far the distance. That would be a GIS question. I may need to do full text analysis on some documents as part of my AI. That would be full text search. Okay. I may need complex indexing. I may even need to use a GPU inside of Postgres, which is actually possible. So you can start to see why you would want to kind of do this potentially in the database. And then finally, I've really shown a very narrow use of AI, specifically a use of AI for user applications. That's certainly a very valid reason, but there are other things we can do with AI. And in fact, there are actually companies formed around Postgres doing this for AI. And I know, Dave, you've done some look at this. Performance adjustments. Could we use AI for optimizer plans? I know there was a talk at 11:30 about feeding back the results from the executor into the optimizer. So similar kind of concept. Index creation, database settings, resource usage. Could these things be improved and reduce or improve performance by maybe having AI solve some of these problems that typically require a person? Could AI be involved here? Things like alerting and for resource exhaustion. Could AI, again, be involved? So I don't know the answer to this. I think we have quite a ways to go. Some problems, I think AI is really good for those intractable problems where we don't really have a good answer. We don't really know, we know maybe what to measure. We don't know how important those measurements are, right? We don't know how significant some of these things that we think are important are. But if we have training data and we can train either machine learning or deep learning to mimic that and potentially give us results, we have the potential to solve some of these harder problems. We're seeing it used kind of basically now. I know there's a huge amount of push around AI, but frankly, the big change that we've seen and the reason AI got so excited, the OpenAI company figured out how to generate. Up until now, AI was typically used for prediction or for predicting a fraud or voice recognition or image recognition. The big change was the concept of generative AI, the concept that AI is now generating text, it's generating images, it's generating videos, okay? That's really why there's so much excitement around AI now. The concept did not change. The thing that OpenAI was able to crack, and nobody other company was up to that point, was the concept of producing output in text format or producing images or videos that really nobody had thought of until that point. I think that's why people are so excited. How important that is, how much that's going to change our industry, we don't really know, but we're going to find out as we go forward. I hope this talk has at least given you a level set of sort of how that works, how the database is involved in this. And I think some of the concepts that are possible, and then again, as I talked about in the beginning, what's realistic for us to expect from AI, and what is really going on, and how do we apply it in a meaningful way for our lives. So I'm going to leave you with this picture. There's a couple of reasons I chose that picture. But anyway, it's a picture of in Phoenix. I'd like to take any questions. Yes? So the question is, if you had an error in how you're computing the weights, how would you correct for that? And this is where I got into that reinforced learning. Do you remember I kind of waved my hands and sort of said, oh, there's a lot of research going on here. What basically happens is that I would say if you have training data and you mismeasured it, you're probably just going to need to retrain it. It's very hard to undo something like that. You could keep feeding more data in and hope that over time the weights will shrink down because over time your new data will influence the weights as much as the old data does. And in fact, there's some logic to say that your new data should be more influential than your old data. For example, for fraud detection, I would say fraud records from 10 years ago are less valuable than fraud records from the last year, right? So then all of a sudden, not only are you loading your data in to set the weights, but you're also giving an importance to the data as it's going in and how influential that data is, it's setting the weights. So some algorithms, for example, will favor newer data over older data. And then over time, as you're continuing to feed it in, you're kind of relearning and you're automatically adjusting to the change in fraud or the change in the way dogs and cats look or the change in how people pronounce certain words. You see what I'm saying? If you've got a reinforced learning, you're going to be doing that, but you have to be careful because if you can set it up so that your new data becomes too influential and therefore it doesn't have enough weight and you start to get really bad results. So that whole reinforcement thing is really a difficult problem. Yeah.
Just a follow-up on that, because I was reading that normally when we introduce new data, there's a model verification process which kinds of verify if the new model does adds to the previous one or not. But then I get into a philosophical problem of what you're saying. If originally the data calculation was wrong, how does the model verification work? How do we verify that the verifying is correctly like doing things and stuff?
That's the thing. It's just some numbers in a neuron. So it has no idea that you've changed the way you're measuring things. It's going to use the old weight and just slightly adjust it for every new data that you train it on. It's going to slightly adjust those weights. So if the weight was way off, then it's going to take a lot of data to get it back to where it is, where it should be, for example. Yeah. And then, again, as fraud changes, for example, you need to detect that, and how do you do that? It's a toughie. Anyway, I'll be up here if you have any questions. I hope you had a good conference. I'm enjoying it a lot. So anyway, thank you very much.
Another round of applause for Bruce. Thank you.
Great.